So the second law, moving on to part 8, which is the second law. And in this, we're going to cover the second law of thermodynamics, heat engines, refrigeration and heat pumps, the Kelvin, Planck and Clausius statements, Carnot cycle and perpetual motion machines. So the first law basically tells us that energy is conserved. So if we think of a cup of coffee that's 80 degrees in a room that's 20 degrees, eventually when the coffee cools down, its energy is migrated to the room. And that's the first law in action. The energy is not in the coffee anymore. It's over here in the room. So we've accounted for it somewhere. But imagine the reverse situation happening. Imagine the energy in the room finding its way back into the cup of coffee again and heating it up. To do so would not violate the first law because energy is still conserved. But we know from observation and experience that this type of process doesn't happen. So we need a second, another law, basically, to cover this situation. And that other law is the second law of thermodynamics. And what the second law tells us is there's some different statements of the second law, which we'll cover, official statements of the second law. We'll cover them later. But it basically describes the nature of energy in the way that it moves. And one way that it moves is from a high temperature to a low temperature, and not the other way around. So it will go from the warm cup of coffee to the cold room, but it won't go from the cold room to the warm cup of coffee spontaneously. But another way energy moves is from a high quality to a low quality, and not the other way around. So an example of that would be, think of a mechanical storing device. You plug it in, the electrical energy is turned into mechanical shaft work, so that starts to rotate in the water. As it does, the water heats up, and that heat eventually dissipates to the surroundings. Now imagine the reverse process. We unplug the mechanical storing device, and we heat up the water externally. As that water heats up, is it going to rotate the mechanical storing device? And the answer to that is no. And the reason why is because work is of a higher quality of energy than heat, to the extent that you can take an amount of work and turn it completely and directly into heat, but you can't take an amount of heat and turn it completely and directly into work. We do have systems that will help us do that. So a system that will help us take an amount of heat and turn it into work is called a heat engine. It needs an energy supply to do that, and we're going to go through heat engines in a few moments. The system that will help us move energy from a low temperature to a high temperature is a refrigerator or heat pump, and that also requires energy in the form of a work input to make it happen. And we'll go through that in the second part of part 8 of the course. So before we introduce the concept of a heat engine, let's describe, first of all, or introduce the concept of a thermal energy reservoir. A thermal energy reservoir is a hypothetical body with a large amount of thermal energy capacity that can absorb or supply heat without undergoing a change of temperature. So imagine putting a small cup of coffee or a small cup of water into a large container of water that's at 30 degrees. If the cup of water is at 90 degrees, it's probably not going to change that large body of water to any great extent. If you had a very, very sensitive measuring instrument, you might detect a small change. So for all intents and purposes, it's a thermal energy reservoir that can give or receive energy without noticing a temperature difference itself. Examples would be large bodies of water. So for example, the power plant down in Poolbeg gives up its energy to water, to the Liffey water, and the Liffey water doesn't experience any change in temperature because it's such a huge, large body of water. The atmosphere, some power plants release their waste energy to the atmosphere, and the atmosphere temperature doesn't change because it's so big in comparison to the small emission of heat from the power plant. Liquid vapor systems that go through the latent heat of evaporation. So as a water boils, for example, it will absorb heat, but it won't notice a temperature difference. And a furnace that's been regulated at a certain temperature can give off heat and supply it to another process without having its own temperature drop. So two types of heat reservoirs. A source is one that supplies energy in the form of heat, and a sink is a reservoir that absorbs energy in the form of heat. So that brings us on to the definition of a heat engine. It's a device that converts heat into work, and it's characterized by the following characteristics. It receives energy from a high temperature reservoir. An amount of that heat or energy is converted into work. Some energy is wasted or rejected to a low temperature sink, and the working fluid operates in a cycle. So once again, a heat engine is a system that performs the conversion of thermal energy into mechanical work. The system brings a working fluid via heat source from a high temperature reservoir to a low temperature state, while transferring heat to the colder sink until it reaches a low temperature state. During this process, some of the thermal energy is converted into work by exploiting the properties of the working substance. So an example here would be water in this piston cylinder arrangement. We heat it up, the water boils, turns into vapor, expands, and moves that piston and does work for us. The steam is then allowed to escape through a relief valve and condenses in the condenser to water. So there's a heat given out to the atmosphere. And then the pump brings that water back into the piston again to repeat the cycle. So we take energy from a low temperature reservoir, reduce amount of work, there's heat given off to a low temperature sink, and the working fluid operates in a cycle. If you can imagine this arrangement in the old steam locomotive engines, you've got the piston here taking the steam, and as it moves, it's connected to these wheels by the crankshaft and rotated, so it moves the old steam locomotive train. Some people regard the internal combustion engine as a heat engine, but strictly speaking, the working fluid's not operating in a cycle. So compared to the book that we work off, it's not strictly speaking a heat engine, because the working fluid is the air and fuel mixture at the intake, and when it combusts, it goes out in the form of gases, not to come back into the system again. Now, the theory about steam engines is quite old, and the internal combustion engine is more recent. So they are categorized in more recent times as heat engines, but don't strictly fall under the category according to that strict definition where the working fluid operates in a cycle. The best example we have is the power plant. We boil up water in the boiler, it becomes superheated steam and drives the turbine. Then the water condenses back down to liquid again, and it's fed back to the boiler. So we're taking energy from a high temperature reservoir, let's say the burning of natural gas or even nuclear reaction. And the amount of work is done at the turbine, and then there's heat given off at the condenser, and the working fluid operates in a cycle. The network out of heat engine is the work that's coming out of the turbine minus the work that goes into the pump to circulate the working fluid. For a system undergoing a cycle in steady state operation, the network out equals the net heat. So the thermal efficiency is the network out over the total heat. So what we're getting out of the system, the form of work, minus divided by the heat that goes in there to make that happen. That's the efficiency. As we've already seen, the network out can be expressed in terms of Q in minus Q out. Mathematically, that can be rearranged or re-expressed as 1 minus Q out over Q in. And what we can see from this equation, that if Q out was 0, this term would be 0. 1 minus 0 is 1, which is 100%. So we can eliminate this step here where we waste energy from the condenser to a low temperature sink, we can make this system 100% efficient. So the question is, can we do that? And the answer is no, and it's because of the second law of thermodynamics. And this illustration is often used to explain it. So we have gas at 30 degrees. It receives energy from a high temperature reservoir operating at 100 degrees. And the gas expands up to 90 degrees. And the purpose is to lift this load, move the piston up to the higher stops, lift this load up and then take it off. So it could be a materials handling system, for example. Now what we want is we want the gas at 90 degrees to cool back down to 30 degrees. For this system to be 100% efficient, we need to move that energy to the reservoir from 90 degrees to the reservoir at 100 degrees. And we know from the second law that we can't do that. We can't move energy from a low temperature to a high temperature. So what we have to do is bring it in contact with a low temperature reservoir and move that energy from 90 degrees to 20 degrees in order to bring it down to 30. So the second law is, in the context, is expressed by a number of different statements. There's two classic statements of the second law, and one of them is expressed by the Kelvin-Planck statement. That was designed or devised by Lord Kelvin and Max Planck. And it comments on the thermal efficiency of a heat engine. And it says, it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So what that means is this system is impossible. We can't take energy from a high temperature reservoir and turn it all into work and then system operate in a cycle. We need a low temperature reservoir for that to happen. In equivalent words, it's saying no heat engine can have a thermal efficiency of 100%. For a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. So what we've established is that we can't have 100% efficiency from a heat engine. We've also established that we can calculate the actual efficiency, the thermal efficiency, by using this very simple equation, 1 minus Q out over Q in. But the question remains, what is the maximum efficiency that we can get from a heat engine? If we know that, we can strive for it. If we don't know it, then we're kind of operating in the dark. So to answer this question, what is the maximum efficiency? We need to introduce the Carnot cycle and the concept of the reversible process. So let's start with the reversible process. A reversible process in thermodynamics is an idealized process that occurs so slowly and smoothly that the system is in near perfect equilibrium at every stage. In other words, a reversible process is one where both the system and its surroundings can be returned to their original states with no net changes in the system or the environment. So an analogy would be a cup of coffee losing its energy to the room and cooling down. But if that energy was to spontaneously find its way back into the cup of coffee again and heat it up, that would be a reversible process. A more practical example would be compressing this cylinder from state 1 to state 2 along this process path. And if we then expanded it back to its original position again along the exact process path, there would be no net work produced, no net heat. And this would be a reversible process that's gone back to its original position and hasn't affected the surroundings by taking or giving heat or work in any shape or form. So a reversible process in thermodynamics is an idealized process that occurs so slowly and smoothly that the system is in near perfect equilibrium at every stage. In other words, a reversible process is one where both the system and its surroundings can be returned to their original states with no net changes in the system or the environment. An analogy would be a cup of coffee at 80 degrees in a room that's 20 degrees. When it cools down and loses its energy to the room, if you can imagine it, the energy spontaneously finding its way back into the cup of coffee again and heating it up to 80 degrees, that would be an idea of a reversible process. More practical example would be a piston moving from state 1 to state 2, compressing the gas. And then during the expansion, it follows the same process path back to state 1 again. So there's no net work, no net heat produced in this system. So it doesn't affect the surroundings in any way. Characteristics of reversible processes, they occur infinitely slowly, allowing the system to adjust at each infinitesimal step, ensuring the system remains in equilibrium. Every infinitesimal change is perfectly controlled with no dissipative effects like friction, turbulence, unrestrained heat flow that would otherwise cause energy loss or irreversibility. Examples of theoretical reversible process would be an isothermal process that occurs at constant temperature. Heat flows in or out of the system and an infinitesimally slow rate, maintaining steady temperature throughout. And an adiabatic process where no heat is transferred in or out of the system. Any changes in energy are due to work done on or by the system, and they happen in a controlled way to avoid any heat leakage. So irreversibilities reversible processes don't occur. They don't occur because of what we call irreversibilities. And the main forms of irreversibilities that occur in our thermodynamic systems are heat transfer across a finite temperature difference, friction, and unrestrained expansion of a gas. Other examples would be the mixing of two fluids, electrical resistance, and chemical reactions. Once they're done, you can't undo them. So let's just take the first one there, heat transfer with a finite temperature difference. So this is where we have a temperature difference, a measurable temperature difference between two systems. And we know that energy is going to flow from the warm temperature, let's say we had a room, energy is going to move from the warm room to the cold room, but it won't move the other way. So it's not a reversible process. One way we could do that is by putting a heat pump in there and absorbing the energy from the cold room and putting it back into the warm room. But that requires a work input, so it's not leaving the surroundings unaffected. It is somewhat true to say, though, if we have, let's say, 500 degrees and 10 degrees, and energy is moving from 500 degrees to 10 degrees, that's an irreversible process. But the closer those temperatures come to each other, so let's say we now have 20 degrees and 19.99 degrees, theoretically, that is a more reversible process. To the extent that if we want to make a process reversible, we can bring the temperatures so close together that there's an infinitesimal difference between the two of them, and theoretically it becomes reversible. And we do have a process, as we've mentioned, in which heat transfer does occur when temperatures are at the same, and they're an isothermal process. So if you think of boiling up water, and when you hit the saturated liquid point and saturated liquid pressure and temperature of water, it's going to want to boil. As you apply more heat to it, the pressure and the temperature stay the same, and all the energy goes into converting the water into vapor. And that's an isothermal process in which there's heat transfer. Friction is an irreversible process as well. So when two objects move against each other, friction is generated. It manifests itself in the form of heat and dissipates to the surroundings and never to be recovered. So in the example of the piston cylinder system where we move from one point to another, if we want to maintain that gas in there and we don't want it leaking, we need a good fit here between the piston head and the cylinder, but we also need a seal in there to make sure that that gas doesn't leak. So now what we have is we've got sliding friction. It manifests itself in the form of heat and dissipates to the surroundings. So going back exactly the same way along this process path is not possible because of that heat loss. Unrestrained rapid expansion of a gas. So the example there would be popping a balloon. Try and unpop that balloon and put the gas back in there. A more practical example is if you had a vessel like this, and halfway down the vessel you had a rubber membrane, and on one side of the rubber membrane you had a gas, a pressurized gas, and then you ruptured that membrane and the gas filled the whole chamber. So how do you get that gas back down one end of the chamber? One way would be to use a piston and compress it back down to the other end of the chamber. But to do that requires a work input, so you're not leaving the surroundings unaffected. So that's another form of irreversibility. Reversible processes move very, very slowly. So because of that, they produce most work for work-producing devices, and they require the least amount of work for devices that require a work input. So if we can maximize the amount of work coming out of the turbine and minimize the amount of work going into the pump, we make the net work as big as possible, which increases our efficiency. So ideal or reversible processes are ones that move so slow that they optimize the amount of work, the network from the system. So to explain that with an analogy, and this analogy is used in the book, so let me just go through it. Imagine you've got a swimming pool full of water and it has a movable side on it on frictionless rollers so that friction doesn't become an issue. So let's say during expansion, we move that side of the wall very fast. If we do that, we disturb the level of the water. We minimize the area of the water impacting upon that wall and helping us move it, which is not useful. During compression, if we move the wall very fast, we disturb the level of water once again, and we maximize the area of the water impacting upon the wall and preventing us moving it, which is not helpful either. So if we were during expansion, for example, to move the wall very, very slowly, infinitely slowly, we would never disturb that level of water. It would drop, but it won't get disturbed. And so we maximize the area of the water impacting upon the wall and helping us move that wall. During compression, if we move the wall infinitely slowly, we also minimize the area of the water impacting upon the wall and resisting the movements of the wall as well. So in those cases, we're reducing the most amount of work and requiring the most amount of work input. So that's the analogy that's used when we're describing how reversible processes maximize the amount of work output and minimize the amount of work input. So just to sum up, during a reversible process, no heat transfer when a finite temperature difference is involved. So there's no heat transfer on a finite, so there's no temperature difference, basically, but there is heat transfer. During a reversible process, no friction is involved. During a reversible process, the ideal gas law is always true for the gas. A reversible process occurs infinitely slowly, and they yield most work and require the least amount of work as well. So they take out all of the inefficiencies in the system. Which brings us on to the Carnot cycle. It was a thought experiment conceived by French physicist Sadi Carnot in 1824, in which we imagine all four processes are reversible, and it provides an upper limit on the efficiency of any classical thermodynamic engine during the conversion of heat into work, or conversely, the efficiency of a refrigeration system in creating a temperature difference through the application of work to the system. It's used as a standard of performance for all heat engines operating between a high and low temperature. So how the Carnot cycle works, and once again, it's theoretical. It's without all of those inefficiencies, and it will help us calculate the maximum efficiency for a heat engine operating between two particular temperatures. So first of all, let's start here. First of all, from point one to do is isothermal expansion with heat transfer. So what's happening is we have a gas operating at temperature TH, which is the same temperature as a high temperature reservoir that it's in contact with. So as the gas expands, the piston wants to move. As the piston moves, TH wants to drop. But if we do this very, very slowly, it doesn't get an opportunity to drop because heat is transferred from the high temperature reservoir. So for all intents and purposes, there's no temperature change, but there is heat transfer. So it's isothermal expansion, in which heat transfer occurs at constant temperature. So that's 1 to 2 on the PV diagram. So 2 to 3, what we do is we remove the high temperature reservoir and we insulate the piston. So now there's no heat transfer in or out of the system. So it's an adiabatic process, and we let the gas cool down from TH to TL. And as it does, the piston moves and does work for us. So that's 2 to 3. Now we look over here, we've 3 to 4. And what happens now is we remove the insulation. We put a low temperature sink in contact with the piston, and we compress the gas with an external work input. And as we do that, TL wants to increase in temperature. But if we do it infinitely slowly, as it tries to increase in temperature, there's heat transfer from the gas to the low temperature sink. So it never gets an opportunity to drop. So what we have is an isothermal compression in which there's heat transfer. And then finally, we take away the low temperature sink and we insulate the piston once again, and we continue to compress it until TL reaches TH, the original temperature. So this is an adiabatic compression where work is done on the system. And each of these processes are theoretically reversible. So we know we can't get a 100% efficiency from a heat engine. We know we can calculate the thermal efficiency from this equation 1 minus QL over QH. But for a reversible heat engine, the heat transfer ratios can be replaced by the ratios of the absolute temperatures in Kelvin of the two reservoirs. So we can go one step further with the Carnot cycle and express these heat transfer ratios in terms of the temperatures of the reservoirs. So the maximum efficiency for a heat engine can be measured by this equation where we go 1 minus TL over TH, TL being the low temperature reservoir, TH being the high temperature reservoir. So here's an example. A heat engine operates between a source at 477 degrees Celsius and a sink at 25 degrees Celsius. If the heat is supplied to the heat engine at a steady rate of 65,000 kilojoules per minute, determine the maximum power output of this engine. So we have our low temperature and our high temperature, but we need to just convert them to absolutes. And when we do, we find out that this heat engine has a maximum efficiency of 60.2%. Now what we want to find is the maximum power based on that efficiency. So we know what the heat transfer rate is. So we've got the efficiency equals the net work over the heat. And if we do that in rate form, we've got the power equals the efficiency and transpose it, the efficiency by the heat transfer. So we have our heat transfer, we just need to divide it by 60 to go from kilojoules per minute to kilojoules per second, multiply that by the efficiency to get the power input, and it's 652.2 kilowatts. Another one, a Carnot heat engine receives 700 kilojoules of heat from a source of unknown temperature and rejects 200 kilojoules of it at 10 degrees. Determine the temperature of the source and the thermal efficiency of the Carnot heat engine. So what we need to do, first of all, TH is determined from the definition of the Carnot efficiency. So the heat ratios equals the temperature ratios. We have the heat ratios, we just need TH. So we have the heat ratios, we have TH converted to absolutes, TL, sorry. From that, then we can calculate TH. And once we have TL and TH, that should say that should say TL there. So the Carnot efficiency is 1 minus TL over TH. So the maximum efficiency we can get from this system is 71.4%. Consider a reversible Carnot heat engine that operates between the thermal reservoirs at 520 degrees C and 15 degrees C while producing a net output power of 60 kilowatts. Determine the thermal efficiency of the Carnot engine, the rate of heat transfer to the engine, and the rate of heat rejection from the engine. So we first convert our two temperatures to absolutes and then put them into our Carnot efficiency. And the maximum efficiency we can get from this engine is 63.7%. So once we know that, this is the efficiency equals the net work over the heat. Transpose that to get the heat on its own. Now do it in rate form. Q dot equals W dot over the efficiency. And now to find Q dot, we put the power out over the efficiency, and we'll find out the amount of heat that comes in from the high temperature reservoir. If we want to know the rate of heat rejection from the engine, in other words, Q out down here, we'll use this expression. W net equals Q H minus QL. And in rate form, it looks like this. And QL, when we transpose that equation, is 34.2 kilowatts. So we've 94.2 kilowatts coming in here. 34 is rejected and wasted to a low temperature sink, but we produce 60 kilowatts of work from the heat engine. The Carnot heat engine receives 650 kilojoules of heat from a source of unknown temperature and rejects 250 of it to a sink at 24 degrees. Determine the temperature of the source and the efficiency of the heat engine. So once again, we have one temperature there. We convert it to absolutes. This is the Carnot relationship between the heat ratios and the temperatures. So we have our heat values. We have TL, so we want TH, and it's 772.6 Kelvin. Then to find out the efficiency of this engine, once we have our two temperatures, it's 1 minus 1 over the other, and it works out at 71.6% efficient. So the second law of thermodynamics has evolved into a rigorous scientific principle thanks to the contributions of Carnot, Clausius, Kelvin, Planck, and others. It encapsulates the idea that natural processes tend to increase the disorder of entropy of an isolated system and has profound implications for understanding energy transformations. So it basically tells us that we can't have a 100% efficient system. But the question remains is how efficient, or excuse me, we can't have 100% efficient, but it hasn't stopped people trying to make systems that are 100% efficient and basically work off their own energy. They're called perpetual motion machines. This is one of an early attempt at a perpetual motion machine. It's called the Robert Flood's water screw. And basically what you have is you have an upper reservoir of water. And as you release that water, the potential energy in the water is turned into kinetic energy as it falls. And that kinetic energy turns into mechanical energy rotating the gearing mechanisms. So the gears are ultimately connected to the water screw over here, which is operating in the other direction and bringing the water up to the higher reservoir. So in theory, all that potential energy will be turned into mechanical energy to bring the water back up again, and it will just keep going on and on. However, all of the kinetic energy in the water is not converted into mechanical energy in the water screw, because some of it is lost in the form of friction in the gearing mechanisms. So eventually what will happen is the high temperature, the upper reservoir will run dry and all the water will end up down the end. So friction is where the losses occur in this system. So perpetual motion machines come in two types or two categories. One is described as perpetual motion machines type 1, and they're ones that violate the first law of thermodynamics. And an example there would be you have a heat engine here, and you boil up the water in the boiler, maybe externally initially, and then the steam drives the turbine. The shaft of the turbine is connected to the pump, so that's how the pump gets its power. Then you have the shaft of the turbine connected to a generator, so it's going to generate electricity and go externally to some supply for some use. But some of that electricity will be tapped off to operate a heating element that will continuously heat, heat the boiler, the water in the boiler. So it'll basically run off its own energy. The problem is when you draw a box around this system here like this and call it a thermodynamic system, what's happening here in this thermodynamic system, you've got energy coming out of the condenser and you have energy coming out in the form of electricity from the generator, but you've no energy coming in. So it's creating its own energy, which is a violation of the first law of thermodynamics, and is therefore regarded as a perpetual motion machine type 1. A perpetual motion machine type 2 is the one that violates the second law of thermodynamics. So here, a simple example would be if we got rid of the condenser from the heat engine. And what's happening then, you've got low-grade steam coming out of the turbine, but we want that in the form of liquid or compressed liquid water, so it can pump back to the boiler. So